guys just reviewing, getting ready for the fourth grade cable quiz. So let's review rapid fire really fast before we take that quiz.
We're just gonna go him.
What is rotate? Yeah, back and forth. All right, so go ahead and close your textbooks. All right, so oxygen. We're just gonna do it just the card side, but keep in mind you don't both direct. Well, no, I'll rotate. All right, what is this one? Nitrogen.
What is that?
Carbon.
Carbon is C.
Yeah, you don't have to see it. I'll just hold it. All right, Zn is what? Good job. All right, neon.
Xe? No, neon is N-A.
Ne. Good job. All right, silicon.
Si.
Si.
That's nickel. No, nickel. It's nickel.
It's nickel. All right, Xe.
Xenon.
Yeah,
Xenon.
xenon. It's how a lot of people. That's how you're technically supposed to say it, but that extra N in the middle is kind of hard to say and pronounce. So xenon is how a lot of people say it fast. All right, copper.
Copper is C-I? No, C-U.
Cu. All right, manganese.
Mn.
Mn. Lithium.
Li?
Li. Pu.
Pu is plutonium.
Good. Cr. Chromium. Au.
Gold.
That's it. Bromine.
Br.
That's it. Tin.
Sn.
That's in. Strontium.
S-T? S-R.
Sr. Put that on the side. We'll try to read it in a minute. All right. Cesium.
Cs.
Good job. Iron.
Fe.
That's it. Sulfur.
S.
That's it. H. Pt.
Phosphorus. PT. To start with a P?
Yep. Put them off the side. You know.
Potassium?
Nope. Platinum. PT. Platinum. Put it on the side. Probably do it in a minute. All right. Rn.
Oh, radium?
Radium.
Radium?
What?
Is it like radium?
You're like getting all around it. Ethan?
Radon.
Radon. Radon. Put it on the side.
That's what it's called.
Radium is what you were
Yes,
saying.
yeah.
You're doing.
You were
Yeah.
close, though.
You were doing some.
You were
weird
right
stuff.
around it.
Yeah. All right. K.
K. Oh, it didn't start with K, does it? Is it supposed to start with
P.
P?
P.
Oh, potassium.
But I can't tell you what name is for the quiz. Just make sure.
Just remember.
Potassium. K.
Special K. Alright.
Okay. Yeah. Oh. Okay. That helps you. All right. Ag.
Argon. No. That's silver.
This is silver. Put them off the side.
Yeah,
Phosphorus.
You know what you do.
Phosphorus, that's
Phos-
is it pH?
pH. Nope.
Phosphorus is the start with P?
Yep.
P.
Yep. It's
What is
just P.
what is pH?
Trying to think of my head. I don't think there's one that's just pure pH. Besides there is like pH scale, but I don't think there's one that's just purely pH. No, there's not. There's not one that's pH. I don't see one right now. Unless I'm drawing like a rule back.
What did it used to be that was pH? There's so many pH.
There's PB. Is that what you're thinking of? Alright. Na.
Sodium.
Good job. Alright. Lead.
PB.
That's PB, so maybe that's what you're thinking of. Alright. Helium.
Ag.
Ag. Ar.
Argon.
That's it. Hg.
Ooh. Hg. That doesn't start with H, does it?
This is a hard one.
What does it start with?
M.
M?
M.
Mercury.
Mercury. Alright. Ca.
Ca, that's calcium.
That's calcium. Alright. Fluorine.
F.
That's uranium.
U.
Good job.
U.
U. Just U. Alright. Barium.
BA.
That's Ca. Chlorine.
Cl.
That's it. Rubidium.
RB.
What was it?
RB.
Rb. That's correct. Cobalt.
Cl.
Co. Be.
Beryllium.
Good job. Mg.
Krypton.
AL.
Aluminum.
That's it.
Which one is manganese? Is that
MN.
MN. Alright, arsenic.
AS.
Yup. Iodine.
Iron.
That's it. And then RA.
RA. Radium.
Yes, I drew a bunch of which one I asked. Alright, let's go over these
You
hard
have
ones.
two radiums?
I have radon and radion. So I think that's the one that you were combining earlier into two of them. Alright, let's go over these hard ones since y'all missed them. Alright, Peachy. Ethan!
Platinum.
Get up. SR?
It's R.
SR.
It's argon?
Yes.
You got this one wrong?
I think both of you got it wrong. Alright, do you remember it? Alright, do you remember it? Alright, this is strontium. Strontium.
Strontium, yeah.
Start off the side. Hg,
Mercury.
mercury. AR,
AG.
sorry, Ag.
That's the one I messed up.
It's not argon.
Isn't it,
Silver.
Silver, silver. Start off the side. K,
potassium.
potassium. Rn, radon.
Radon.
Radon. So Sr,
Strontium.
strontium. Ag, silver. Rn, radon. Alright, take out one piece of paper, pen and a pencil.
We mostly got it right.
How many, what are we numbering it to?
You get a printed one today. So this is actually part you're actually going off Becca one. But they're giving you 20 blanks, so each one is worth 5 points apiece, so it's a little bit easier than like missing one and losing a whole letter grade. You have to miss 2 before you lose a whole letter grade.
Consider it a hard quiz.
What?
Consider it a hard quiz.
I have no idea actually.
Like,
So
not really.
what?
Do you like this dude?
studying now?
It just depends because I mean there's no like for like the top part where it says short answer, write the chemical symbol, there's really no spelling credit, so you either gotta get it or you don't. Because I mean if you put down the wrong letters then you put down the wrong letters, I have to go off what you actually wrote for it. So pay attention to what you're doing. So short answer, write the chemical symbol. So that's the symbol as you've been learning it. Remember the first letter is always capitalized, second letter is not. I don't know if I've harped on that too much, but that's just tradition. So just make a note of that as you're being careful throughout it. Second section, you're writing out the word or the name of the element. So pay attention to what you're doing. Just be careful. Jamie and Quentin, you should have that quiz in your packet that was given to you. So if you need to pause to go get it from your proctor, you can. Just psyching yourself out, just think through. checking your stuff out, we have gone over this, and I'm sorry, you're just, what?
Yeah.
We have,
I did.
yeah. Okay, just think it through, yeah, just think, okay, what does it have to be then? Just try to think through it, I can't tell you right now, we can't talk about it after the quiz, in case Jamie and Quentin have to go and they're a little bit behind getting the quiz, we can't talk about it, but you can look in your book later and see which one it is. But yeah, we've gone over it. You're just having a mental block right now. I can't tell you what it starts with. You're just having a mental block. Yes, maybe you'll be right. Jamie and Quentin, if you need another minute or two because you had to go get it from your proctor, that's fine. You can pause the video and finish it up, but we have to keep going from it. So, you go ahead and get out your textbooks now as I go around and collect the quiz from it. Alright, so go ahead and take out your textbooks and turn to page number, kind of left off talking on page 31 and 32. We've gone through some of the practices for it, but not a lot. Now, you don't have a second quiz today. You are going to have one Monday. So I'm telling you right now, because I don't really like Monday quizzes, that you're going to have one on Monday. So just make sure that you are studying and prepared. Yeah, I know, I'm sorry. We can't talk about it right now because of the quiz. But yeah, so just make sure that you're studying for it. The periodic tables will be on your test. So make sure that you are studying them. Don't just think of, okay, that's done. No, they're going to reappear. So make sure you're going back and looking over it. Alright, we talked about atomic number versus mass number versus isotopes versus ions. Alright, what determines the identity of the element? What determines the number of what? Ethan? Nope. So, protons, neutrons, electrons determines the identity of the element.
What?
Protons, neutrons, electrons. Which one determines the identity?
Protons.
Protons. So, if you were, my track table is down, so I can't gesture to it anymore. But if you were to look at oxygen, oxygen has how many protons? Chris, I know it's in the back of your book. It's on the very back cover, like on the back of the inside. So oxygen, it's in that top, like little second row. You want to go, if you look at the little baby row. Alright, how many is that? 8. Good job. So, I almost wrote highlighter on my board. So, oxygen always has 8 protons. If I were to take away one, and I would go to, if I were to go down or take away one, what would it become? Ethan? What?
Oh, what?
Yeah, just use your back cover. My tech table's taken down for right now.
Nitrogen.
Yep, and then if I were to add a proton, what would it become? Chris? Okay, and then if I had oxygen and then added one more? Fluorine. So that's the idea of oxygen. Always has 8. Always. We represent that with a Z. Alright, the mass number is what then, Chris?
16.
Okay, typically you're right, but yes, it is typically 16. But where, like, the 16 is the number of what then? So half of them have to be protons. What's the other half then?
Protons?
Okay, half of them are protons.
Oh,
8, yeah.
Neutrons?
Neutrons. So remember, this is the mass number. This is protons and neutrons together. What's that name we use to refer to protons and neutrons together, or stuff in the nucleus together? Ethan. I know this is from like 2 days ago.
Start with a C.
Starts with an N. It's like, it's kind of like how boyfriend and girlfriends, they'll hyphen their names together. So what do you call protons and neutrons together? Okay, Chris? Nucleon. So this represents the nucleon. So, and of course I had it on the board as well. But yeah, so nucleons, this is the number of protons and neutrons together. So for this one, since oxygen has to have 8, if I have oxygen 16, I have how many neutrons then?
You have oxygen 16, you
Yeah.
have 8.
Yeah, so that's because, remember, if I were to say oxygen 18, I'm referring to that this particular type of oxygen has 16 as a mass number, the number of protons and neutrons together. Let's say I have oxygen 15 as a side note. So this could happen. Alright, so if I have oxygen 15, how many protons do I have?
8.
8. So I always have to have 8. How many neutrons do I have then?
That's me.
Yep.
7.
7. So, what is it called then whenever you have a different number of neutrons for the same element? That's the isotope. So just make sure you're going back through it thinking, okay, this makes sense. We're coming through it. I know Jamie and Quentin, you can't see probably my gesturing too very well because of the angle, so I'm sorry. But isotopes and elements, a different number of neutrons. Alright, so if I were to have oxygen like this where it is a neutral substance, how many electrons must it have for it to be neutral, Ethan?
8.
8. Why?
Because of that they both equal 16. 8 and 8. 8. 8 protons.
Okay, I see where you're coming from, so you got lucky in that. But okay, but what part of the atom is the positive charge? Protons, neutrons, electrons?
Protons.
Protons. So if I have 8 protons, what's the total positive charge?
8.
Okay, positive 8. Alright, now, if I just have the 8 protons and a positive 8 charge, will my atom be neutral?
Yes.
There is
Oh, neutral. No.
Okay, so how many negative charges do I have to add for it to equal 0 or neutral?
8.
Yep, so you were right with the idea of you need 8 electrons because each little electron is worth -1. So you got lucky in the idea of thinking, okay, 16, but it's the idea of because this has a positive 8 charge because of the protons, then if I have a neutral substance, I have to have 8 electrons to balance it out. Okay, anyone have any questions about that? Alright, let's practice this where we left off. Last class period, look over on page number 32. And then practice it. Let's do the examples at the top of the page and then we'll do the application. So example A, example 2.18, write the nuclear symbol for the isotopes of silicon having 14, 15, and 16 neutrons respectively. Alright, so we're talking about silicon. So silicon has how many protons? You have to use your book for this one.
14.
14.
Where'd you find silicon?
It should be if you're at let me put it in order of the periodic table. So find 14 and silicon should be right
Under
there.
carbon.
There you go. So silicon has 14. Alright, so it has 14 protons. So it says to write the nuclear symbols for the isotope of silicon having 14, 15, and 16 neutrons respectively. Alright, so if I have 14 protons, and then I'm gonna add 14 neutrons to it, what's the total mass number? 28, so that's the first one for it. So it says, what about if there's 15 neutrons? What's the total mass number?
29.
Alright, and then there's 16 neutrons.
30.
30, so yeah, it's just making you go through it, just checking. Alright, B then, B's a little bit harder. Every isotope, how many protons, neutrons, and electrons are in each of these isotopes? So for this one, it's argon. So it's asking how many protons, how many neutrons, how many electrons. Alright, so argon, how many protons?
18.
Alright, how many neutrons? You have to do fast math.
42.
22. And then if it's neutral, how many electrons?
It's gonna be neutral.
It's neutral. Then we'll assign a charge. So how many protons?
6.
How many neutrons? How many electrons?
6.
6. Good job, because there's no charge written. Alright, I'm going to go over here. Am I still in the shot? I'll write it down here. So, iodine, 53, 131. Alright, so how many protons?
70.
Oh, what protons? Protons. 53. How many neutrons?
Keep it zeros for a second.
You have a calculator.
Oh yeah, I do. 78.
78. And then how many electrons? It's hard. It has a -1 charge. Sometimes they'll just write a negative sign or just -1, but it's an understood one with a negative sign. 54. Perfect. Alright, do we have questions about that? Alright, let's do the application then on page 32. The actual completion application number 1. We'll do that one first. So complete the following table. The first row is done for you, so it's giving you an example with helium first for it. Now remember, Z stands for atomic number, A stands for the mass number, N stands for number of neutrons. So it's just telling you what the different symbols are for it. Alright, so this first one, actually, I'll give y'all 2 to 3 minutes. Try to see how much of it you can complete by yourself, and then we'll go back and we'll check. This will give me time to write on the board.
Wait, what is A mean?
A is mass number. So protons and neutrons together.
Oh, yeah. Protons and neutrons together?
Mass number is A.
So what is N?
Neutrons.
So we just write, for the second one, we just write 207 in A?
Yeah, because that's the total mass number.
Oh.
You said just do number 1?
Yeah, if you want to get started in number 2, you can. Because if we don't have time, then it'll be part of homework. So if you want to go ahead and get ahead and jump on it, you can.
What does it want us to do in number 2?
Alright, so complete the following table. The first row is done for you, so it's giving you again an example one. Alright, if it tells you the mass number and the number of neutrons, what can you use to find out and to figure out?
You just subtract the 42.
Alright, and that'll tell you the number of what?
The number of
Okay, what's Z? Alright, and it's the number of protons, and once you know the number of protons, what can you find? The identity of the element. So that's how come they've worked it that way for you. Alright, anyone still working on application 1? Alright, let's go over that one. Alright, so let's look at lead first off. Alright, Chris, what do you have for that first? Oh, I copied down helium, I didn't need to. Alright, so for lead, what do you have for the for the atomic number?
82.
Good job. What do you have for mass number, Ethan?
207?
That's it. What do you have for the number of neutrons, Chris?
125.
Good job. Alright, number of electrons, Ethan?
P2?
That's it. And the electrical charge?
0.
0, because it's neutral. Alright, so we'll start doing again. Alright, the atomic number is what then? So Z for boron.
5.
That's it. Ethan, what do you got for mass number?
110.
Whoa.
10.
10. Okay, 10. And then the number of neutrons, Chris?
5.
Good job. So then the number of electrons, Ethan?
5.
And then the electrical charge, Chris?
0.
0. Alright, silver. What have you got for the atomic number, Ethan?
47.
Good job. What do you have for the mass number? Chris?
109.
Good job. What do you have for the number of neutrons?
62.
Alright, what do you have for the number of electrons?
46.
Good job. So what do you have for the electrical charge, Ethan?
Plus 1.
Good job. Alright, you have any questions about that one? That was perfect. Alright.
Let's put plus on for the
Yeah, because it's understood +1. Alright. We'll let y'all get started on number 2. I'll give you another minute or 2 and then we'll check it. This is more thinking. You need to have practice, because if you were to say, see this on your test, would you know what to do? So I've got to go over this. Make sure that you know that you know that you know. it's okay. Alright, so what, for that first blank where it tells you that the mass number is 235 and the number of neutrons is 143. So you remember, this is the total of protons and neutrons together. So if this is the neutrons, you can just subtract it and figure out the number of protons. Once you can find the number of protons, you can find the identity of your element. Alright, so what do you get for number of neutrons, Chris?
Neutrons for which
I'm
one?
sorry, number of protons for that first blank.
92.
What?
92.
92, and that's what element?
Uranium.
Good job. So uranium, 92. Now this one, it says, has an electrical charge of 0. So how many electrons does it have to have then, Ethan?
143.
Oh.
Wait, what?
Okay, we're at the blank one. So underneath silver, as the example, we're on that first whole line where it's blank. So it's uranium.
92.
What?
92.
Good job. So it has to have 92.
I was
Somebody
mixed up.
What?
I was mixed up
It's
something.
okay. So 92. Alright, so it says, the next one is iodine with a negative sign. So if it's iodine, how many protons does it have to have?
53.
Good job. So it has 53, and it has the mass number of 126. How many neutrons does it have to have?
73.
Good job. So this one is this one has a negative 1 charge. So how many electrons does it have to have?
52.
What?
52. 52.
Alright, so if I have 53 protons and I have to have a negative 1, 53 plus how many negatives will equal a negative 1?
54.
54. You just went the wrong direction. You had the right idea, just wrong direction. So 54. Just make a note of that, but yes, it's a negative 1 charge. Is that what you got, Ethan?
Yeah.
That's it. Alright, so the next one, it says the atomic number is 16. So if it's 16, what's the element? Sulfur. Alright, and it tells you that the number of neutrons is 20, so the mass number must be what, Ethan?
4.
Alright, if it's,
Don't say huh. I haven't done it yet.
it's okay, you worked faster, you get a little bit of a head start. So, if it has 16, and it has 16 protons and 20 neutrons, so together it's
36.
36. So 36 for 8, so that's the mass number for it. And then it tells you you have an electrical charge of negative 2. So if I have 16 protons, but I have a charge of negative 2, how many electrons do I have? Okay, even?
14.
Okay, so this is
Oh,
positive.
no, wrong way. 18.
18. Alright, so just think of, okay, protons can only be positive, electrons can only be negative. So if I can't change the number of protons, how many electrons do I have to add or subtract in order to get the correct number? How many negative things?
So,
Alright.
in other words, I can get this right if I have more time.
Yeah,
It's pretty easy.
Yeah, it's one of those, we just went quick, but again, I have to make sure I'm trying to cover everything. My goal is that we can get through most of this today. I want to watch another lab on Monday, but again, it depends how fast we're moving for it. So, nope, it's okay to where I'm trying to basically, I want to make sure you know all your math and stuff though, before we get to Monday and Tuesday. So if you're confused on something, ask now, because I don't potentially have a whole lot of time next week. We're going to review Tuesday, but that should be it. But there's a lot of math in this section, so I want to make sure. Okay.
Can I tell you something?
What?
Guys, it's also be equal to me.
Nope, wait. The class is going to be over in like 15 minutes. Just hang on. Alright, so look over on page 35. So the atomic mass and atomic mass unit. Alright, so what is the major unit for measuring mass? We talked about this like way back in chapter 1.
Atomic mass unit?
Okay, for if you're regular, like a regular object, what's the major unit for mass?
Oh, isn't it liter? No,
That's for
it's
both.
not liter. Is it, gram?
Gram. Now, since atoms are so small, measuring them in grams is so cumbersome because that's a large unit compared to how small they are. So science said, okay, we come up with a whole better term for how much that these individual little atoms weigh. So we're going to use atomic mass units. Your book gives you the symbol U. That's slightly dated. So if you want to write AMU off to the side, that's a number symbol for it. They get more into that into physics. So again, AMU or just U, I'll take either symbol for it, that's fine. But this is the more modern one, so AMU or U, either one is fine for it. The atomic mass unit is defined as exactly 1/12 the mass of a carbon-12 atom. So they said how much a carbon-12 atom weighs. So whenever you
What's
have,
AMU?
wiggle it, what?
What is AMU?
That's the atomic mass units. That's the unit. So instead of using grams, they're going to use the atomic mass units. What they did is they said, okay, we're going to have a carbon-12 atom. So if it's carbon-12, how many protons does it have? Alright, how many neutrons does it have?
6.
Alright, so they said, okay, we're gonna take that this one has 12 parts, basically 6 protons, 6 neutrons. We're going to divide it by 12. We're gonna say, basically, this is 1 atomic mass unit. So it's 1/12 of the carbon-12 atom. So they just picked that as this is the definition of the AMUs, the atomic mass unit. It's like grams, but it's a much smaller scale. So kind of like going from a foot to an inch. An inch is a smaller piece of a foot. Same idea. But they took grams and they said grams is just too large to work with atoms. So we're going to chop it down to a much smaller section. Just make a note, AMUs, that is the atomic mass unit. So that's the unit that they use for it. Okay, do you have any questions about that now? Okay, so just make a note, an atom's atomic mass measured in atomic mass units is approximately equal to the atomic's mass number. So again, since this is the number of protons and neutrons together, most of the time your atomic mass unit will match up pretty close to it. There is some slight discrepancies, your book points out as well. Whenever you have atoms combined together, they will generate energy, and because energy comes from mass, it'll get changed slightly, so you lose a little bit of mass. The electrons add a very small amount of weight to it, so because of that, it's not a perfect condition. So if you have carbon-12, it doesn't mean it's going to weigh exactly 12 atomic mass units. It might be really, really close, so this is a good approximation for it. So just telling you the atomic mass units is typically really close to the mass number. So it's a good ballpark average to figure out, okay, the atomic mass of a substance, like for oxygen in particular, you memorize oxygen just because oxygen you use so much. Oxygen has 8 protons. Typically, you see oxygen like this, because you have oxygen, whenever it has 8 protons and then 8 neutrons altogether. The atomic mass is this. Now, oxygen falls out perfectly, but it's the idea of this would be the atomic mass units for oxygen. They're not always whole numbers like this, though. They might be slightly more, they might be slightly less in round. But it's the idea of typically you're going to have the mass number be a good approximate over what the AMUs or the actual weight of an atom is. Alright, any other questions about that? Alright, mass spectroscopy. So they're trying to figure out how do we determine this and what do we do for it. They would use the gas of an atom. So they would take a pure substance like oxygen or like the gas. They would look to see, okay, once we give it a charge, we want to see how much the individual pieces weigh for it. So they would take the gaseous sample and they would ionize it or give it a charge, and then they would speed it up through this device. Now, you're going to know, oh, that's the example for it, not the actual device. You're going to notice this later on, and you might remember from physical science, that electricity and magnetism relate the two ideas. Electricity can cause magnetism. That's part of the reason why magnetism affects electricity. So they would have the gaseous sample, they would give it a charge, and then they would accelerate it or speed it up. And then they would send it through a magnet. Since the magnet affects the electricity, it'll cause them to basically shift or get pulled apart from it. So the gaseous sample would separate out based on the ions, what the individual kind of weight for it. All the ions of the same charge experience the same force from the magnetic field. So the heavier ones would be moved not as much as the lighter ones. So because of that, we would get a record of the mass distribution of the particles in the sample. We would get a mass spectrum. Your book gives you the table or the picture of the mass spectrum of neon. You don't have to know this. Now remember, this is just neon. So they're saying the individual atoms of neon, some of them would be heavier than the others. So scientists were knowing, okay, we don't have just this pure isotope of neon. We have a bunch of different isotopes of neon on the inside of it. So they're saying, okay, some of them weigh more than others. So again, using this as an example, they would just say, okay, we would take a substance, give it a charge, run it through acceleration plates, curve it underneath a magnet, and they would see them separate out with the heavier ones and the lighter ones. Your book gives you the analogy of wind in a car or wind surrounding a car. That if you've driven before in really windy weather, all right, how many of you can drive, or your parents are helping you like practice driving? Okay, how many of you have driven on the highway before in windy weather? How was it, Chris?
You could just feel it, like it was bumping the car.
Yeah, typically, depending on how strong the wind is and your car size and like how heavy your car
I drive
is.
a truck, so.
So yeah, so you might not notice it as much because typically trucks are heavier than like a regular car. Yeah, so I mean that's a decent sized truck. Now for my car is not aerodynamic. If you've seen my car is light for its size and it's tall for its size. So I can feel the wind very strongly in my car, because my car is small, light, tallish, kind of cube-shaped car. So I can feel it because it catches the wind. Driving down the highway gets kind of stressful some days, whenever it's super windy, because I can feel the wind shaking my car. Now, if you're a heavier car or a heavier truck, you might notice it, but you're not going to blow off the road. So that's the idea, and that's what video is trying to show you. This is the same idea, that if you have a heavier car or a heavier truck, you might notice it, but you're not necessarily praying hard. For me, depending on how much wind there is, because I have a lighter car, I have a tendency for my car will actually start to kind of drive or shift a little bit as it's pushing my car. So for this one, the lighter cars, they're more affected by the wind. That's the same idea with the mass spectrometer, that whenever they shoot them with the ion, with the charge, and then have a magnetic field, the lighter ions get pushed way over, while the heavier ones don't. Some of them scientists are noticing that, even though we have a pure substance of neon, we're having it separate into its different ions or the different isotopes. So we start noticing, okay, just because we have carbon doesn't mean it's carbon-12 over and over and over again. This is carbon, so it has to have the same number of protons, but some of them are heavier than others. So we have a whole bunch of isotopes in a sample. So other scientists are saying, okay, we have to figure out then how do we figure out the average. If not all carbon is the exact same, then how do we figure out what do we put for the AMU? How do we decide? They decided by the average atomic mass or the weighted average, technically. So flip over to the next page. Weighted average is how they technically decide it to figure out what the average atomic mass is. Not every single oxygen weighs 16 AMUs exactly. Some of them weigh more, some of them weigh less. Christian? That's good.
Like comparison, how how many of those would it take to be in a pound?
AMUs? Ooh, a pound of pure oxygen? A lot.
Like billions?
I would say yes. Yes. Because a cup of water itself has 76 times, I just watched a video on this with physical science, 76 times 10 to the 24, I believe, individual molecules. Like, these are super tiny. That's why we give them a whole different unit.
If you could see atoms in the air, would you be able to see anything else besides the atoms? Like I'm saying, if the atoms were visible, like, would it block your vision completely because of how many atoms there are?
Well, I mean, technically, whenever you look at the dish, you're looking at the atoms technically of this. But if you could see it to where you could see the individual spheres, you would have to be microscopic. So you wouldn't be able to notice it's the dust. You would just notice, whoa, there's a whole bunch of stuff. You wouldn't be able to tell it's a dust at that point.
It would just be there's individual little spheres.
Yes, loosely. We're going to talk more about how an atom actually looks later on, but yes, loosely. It's a whole bunch of little bitty circles, itty bitty ones, and it's all the charges holding them together with cohesion. We're going to talk about it, how they actually look later on.
In this.
What?
There's circles in this.
Okay. Roughly, as how we think of it, a bunch of itty bitty tiny circles all hooked up together. But there's kind of how on your computer screen, it's made of itty bitty little squares or pixels, and it makes a giant image. Same idea. Itty bitty little bitty circles makes up your disk. Now, when we talk about it, this gets into particle physics and other theoretical stuff because scientists can't see it a lot. So it's one of those. It works out on paper and it works out in experiments. So it seems like this is the best guess for theory-wise. Wait till you hit the uncertainty principle. That's fun. This is one of the ones where it's one of those we can't actually test this, but it seems like it works. Yeah, this is one of the reasons why science is
there any
interesting.
microscope that's big enough to see the individual atoms?
They have blown up yes, they use electron microscopes to see how it works, but there's problems with that because of Heisenberg's uncertainty principle. Once you shoot it with light, shooting it with a photon of light stops it because you basically crashed into it with light, and since light is so small and the electrons are so small, that basically stops it because you basically slammed into it, so you can no longer see it moving. So you basically not killed it, but you've made it be stationary now. What?
Are they expensive?
They're really nice ones, yes. Alright, we gotta keep going on. So, weighted average, make it up for this. Weighted average is used to account for the natural abundances of the isotope. Alright, the best way to explain this is to use their example for it. So, to demonstrate this concept, suppose a high school track team consists of 6 runners with a mass of 60 kilograms each, and 2 shot putters with a mass of 80 kilograms each. What is the average mass of each track team member? So they're not asking, okay, what's the individual mass of each individual member? They're saying, okay, for the collective team, what is the average mass altogether? What's the average weighted average? So based on number and based on each individual guy's weight, what's the average for it? So how you figure out this is you can't just say, okay, there's 8 members of the team, some of them weigh 60, but then some of them weigh 80. So you can't just say 8 times this and divide. You can't just add it up together and just divide like a regular average, because there's 2 of these and there's 6 of these. So it's not an even distribution. So what you do for this is you have to factor in the number times their weight, add it to the number times their weight. So you have to add everybody's individual weight and then divide, so you add it up together and then divide the total amount by 8 to figure out what the weighted average is. Your book gives you a couple different ways to write this out. I like the top one the best. That one makes the most sense to me. So if you were to set it up like a giant fraction, it's the 2 times the 80 kilogram shot putters plus 6 times the runners, so 60 kilograms, divided by 8 total. That'll give you the weighted average. So it's a little bit different than a regular average because you're taking into how many of each substance you have. So the answer to this would be what, Ethan? 65. Now keep in mind, is anyone on the team actually weighing 65 kilograms? No, but it just said, what? Well, they said that each of the guys on the track team, as like the runners, each of them exactly weighed 60, like as an example, small like people. So it's the idea of, okay, here's the example for it. So no one actually weighs 65 kilograms, but it's the average, weighted average, if you're talking about the entire team all at once. So that's what your book's saying, and that's how scientists say that, okay, here's the weighted average of oxygen. Oxygen has 8 protons and then 8 neutrons. So the weighted atomic average, if you're talking about all of the types of oxygen that we find occurring in the earth, by the time you factor in all the different isotopes and add them up and divide it all up, we say we get an average, a weighted average of 16 AMUs. Some individual oxygen atoms might be slightly heavier because their isotopes are slightly lighter. But based on how often we find them, that we're going to give them a weighted atomic mass of 16 AMUs. Alright, anyone have any questions about this concept before we practice? Because typing it in your calculator can be a little bit hard.
Yeah.
Alright, let's look at the example at the top of page 35. So, calculate the average atomic mass of a neon gas. If naturally occurring neon is 90.48%, then it gives it to you. 0.24% gives it to you. And then 9.25% gives it to you. Alright, your book tells you in that example how to solve this, so I would write the steps on the side or highlight or make a note to start, because that's where it's telling you how to solve this type of problem. The first thing you want to do is change the percents into a decimal fraction by moving the decimal point 2 places to the left and dropping the percent sign. You might remember this from elementary or from basic math, that if you have a percent and you need to change it into a decimal, you move it 2 places to the left and your percent sign gets dropped. This is not what you can calculate in your calculator. So 90.48% becomes 0.9048. 27% becomes what then? Chris?
Wait, what?
Alright, so if I have 0.27%, I need to change it into a decimal. How do I move it, Chris?
0.27.
So it's already 0.27.
0.0027.
There you go. So and I don't percent. Alright, and then if I have the last percent, we'll say it's 9.25%. Alright, how do I change this one into a decimal?
Move it 1 time. Up to the
There.
left, yeah.
Just here. That's percent sign.
Move 2 zeros or something?
Okay, so
I
remember,
didn't get it the first time. Like, I didn't hear what you said.
alright, whenever you have a percent, like let's say you have, we'll still do this one. So if it's 9.25, whenever you're canceling out on the percent, you're going to move it 2 places to the left.
Okay.
So 0.
95.
Yeah, I'm sorry, 0.095. I put my decimal in the wrong spot. Alright, so that's just how you change a percent into a decimal. Anyone have any questions about that part? Because there's one been a while for basic math. Alright, now for this one, you're going to multiply the percent for times each isotope. So that first one is 90.48%, and you're going to use the atomic mass units. Now, these numbers are very small, because you wanna be careful with your calculator. You probably wanna multiply it in parentheses in your calculator, cause your calculator's gonna kinda get confused. So, 0.9090, oh, it's like a 4. Oh, it's supposed to be a 4. Well, it should be me. 48 times, it's times the point, sorry, 19 point, I'm not gonna finish this, 992. You're going to multiply these two numbers together and then add it to the next percent times the next number of isotopes. So the next one for the 0.27%, it has 20.994 as the atomic mass unit. You add all that together, you multiply these two together, and then add it to the next one. So 0.09, I lost my spot, 25, 21.991. And we're gonna talk through this on Monday because I'm gonna run out of time. So you're gonna multiply these two together, add it to this product, add it to this product, and that'll tell you what the total average is, weighted average for it, the whole thing for it. So again, we'll talk through this more on Monday because I'm just about out of time. Alright, your homework for tonight? You're going to answer on page 36. You're going to do problems 2, 4, and 5. So on page 36, 2, 4, and 5. Try to figure out 5 with your weighted average by yourself. If you're completely stuck, still try. But then I'll help you out Monday. So I don't have a whole lot of time depending on how much we can go through. And remember, you have a quiz on Monday, so don't forget, quiz on Monday as well.
Multiply the first two, add the next two.
Multiply, 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 add all of your products together. So the answer for this one, add the answer for this one, add the answer for this
If
one.
I were to find it like that, I can multiply and then take that, and I can multiply all of them and then add it. Like multiply one row, multiply the next row, multiply the next row, and
Ethan,
add
And
them.
then add them all together? Yes.
This can be
That's what
brain
you do. What?
I'm saying, Ethan, you're gonna be burning it. You have more classes. You have to go.
Okay, be sure to be nice, Chris.
Yeah.
Be sure to be nice.
I'm being a very nice boy.